Hello! I'd like to start a weekly video series where we recap the material that was covered in the previous week. Obviously, it's just a quick review of all the big topics, so I won't be able to cover everything. And hopefully we can go through a few examples during these short lectures as well. And what did we do this week? Well, we started off with sequences. Right? We're beginning this final unit of the semester. And what is a sequence? Well, a sequence is really intuitive. It's just an infinite ordered list of numbers, right? So, an infinite ordered list of numbers. Okay, so something like, I won't even give you the numbers here, we'll just say A1 is a number, and then A2 is a number, A3 is a number, A4 is a number. So here's an infinite ordered list of numbers. When I say ordered, I mean we have to respect the order that I give you these numbers in. Sometimes people put curly brackets around their sequence, so I'll do that here. But this is all that a sequence is. It's an ordered list of numbers. So here's an actual example. How about this guy? Here's my sequence going to be 1, 1/2, 1/3, 1/4. Obviously the next term is 1/5 and then 1/6. Sometimes people dot this out and they just tell you the nth term. So once you understand the pattern, the nth term is 1 over n, and then this continues on forever. Right, so some sleek notation people use is if you understand what the nth term is, then they'll just tell you my sequence is the sequence 1 over n, where do I start? Well, n starts at 1, and then it goes on to infinity, right? So n equals 1, off to infinity. So there's my sequence, and what we really care about with sequences, one of the most important things about sequences is what happens as you go out really far in the sequence, right? What happens if I let n go off to infinity? Well, in this case, it's kind of clear, right? As n gets bigger, these terms, 1 over n, are getting smaller and smaller and smaller. So pretty clearly, as I go out really far in the sequence, it's tending towards 0, right? So we would say that this sequence converges. This is the terminology we use. If it approaches a fixed number, this converges to 0, right? Because 1 over n is indeed tending to 0 as n goes off to infinity. If a sequence doesn't converge, if it's not approaching any particular fixed number, then it's said to diverge. Right, but how do we get this? How do we get this result so quickly? Just intuitively, how did this tend to 0? Well, what you're probably doing is this, right? Maybe without even realizing it, is you're just replacing this with a continuous function in your mind, right? So this is what a sequence really is. If I plot this sequence, a sub n being 1 over n, so I've got 1, 2, 3, 4, 5, 6, and so on. Right, if I plotted these values, if I plotted them, here's 1, there's the first term, right? A1 equals 1. The second term, when n is 2, we've got 1/2. So A2 is 1/2. The third term is 1/3, maybe like right there. The fourth term was 1/4. I'll stop writing them because I'm running out of space. Fifth term was 1/5, then 1/6, and so on. So what a sequence really is, a sequence is actually a sub n, that's really just shorthand notation for a of n, right? And what a sequence is it's a function, but it's not the type of function you're used to. It doesn't sort of transform all real numbers into other real numbers. It's only defined on the integers. It's this discrete function where I'm only allowed to plug in 1, 2, 3, 4, 5, 6, and so on, right? So it's a function. Formally it's a function, but it's a discrete function that only exists at the integers. Right? But when we observe that this tends off to 0, right? as n goes to infinity, what you're probably doing is just imagining this is a continuous function, right? It's defined on some continuous variable, 1 over x instead, right? So I've got this continuous function that agrees with my sequence. It just runs through these points. So here's y equals 1 over x. And you're probably just applying your calculus 1 knowledge for these continuous functions and saying, well, I know 1 over x goes to 0, so 1 over n must do the same thing. And it turns out with sequences, you're usually allowed to do this. This is fine. You're allowed to just replace your sequence with a continuous function instead. And ask, what's my limit in this case? And this is really powerful, because it says that all of our stuff from Calc 1, L'Hopital's and whatnot, we're allowed to use it. Right? For example, here's my sequence. I'll just tell you the nth term. The nth term will be n times sine of 1 over n. Alright, so this would be the sequence. If n is 1, we'd have 1 times sine of 1. Second term would be 2 times sine of 1/2. Third term would be 3 times sine of 1/3. And so on. And my question is, does this converge? Is this approaching any particular value? And it might not. But it also might. So the question here is to look at this. And what you'll notice is if I pretend this is just a continuous variable, say x, as x or n goes off to infinity, this is going to infinity times sine of 1 over infinity, so sine of 0. So this is actually one of these 0 times, infinity times 0 indeterminate types. Right? The n is trying to blow the function up, make it very large. The sine of 0 is trying to make the function very small, try to shrink it down to 0. They compete against each other. In the limit, it's not clear which one wins. Right? But that's okay, because we have L'Hopital's that comes to the rescue here. Right? So you have to remember how L'Hopital's works for all of our different indeterminate forms. For 0 times infinity or infinity times 0, there's a trick we always use, which is rewrite this function. Rewrite it as one function divided by 1 over the other one. Usually you keep the more complicated stuff up top, so sine of 1 over n. I'll write this as sine of 1 over n over 1 over n. Right? It's the exact same function, just written algebraically in a different way, because if I wanted to carry out this division, I would just flip it and multiply, right? And the reason we did this is because now this is type 0 over 0. So I can use L'Hopital's, which says my limit is going to be the ratio of derivatives instead. So let's see. So the limit of a sub n as n goes to infinity is actually the limit as n goes to infinity of the ratio of derivatives instead. So we'll differentiate this, and what do we have? We're going to have cosine of 1 over n. Right, derivative of sine is cosine, inside stays the same, but now using the chain rule times the derivative of the inside here, derivative of 1 over n, check this if you want, is minus 1 over n squared, over the derivative of the bottom, and we just differentiate this, derivative of 1 over n is minus 1 over n squared. These minus 1 over n squareds cancel, and as n goes off to infinity, this is approaching cosine of 0, which is 1. So the answer of does this sequence converge, the answer is yes. It's just asking this binary question, does it converge or not, yes or no? Yes, it does. And I can actually tell you what value the sequence converges to. It converges to the value of 1. Okay? So everything you know about limits in the past, you can apply it here. There's a few really common sequences, or let me not say sequences, but a few really common limits that are worth memorizing so you don't have to do tricky L'Hopital stuff all the time. Two very common limits worth memorizing. 1, the limit as n goes to infinity of n to the 1 over n, right, which is of course sometimes written as the nth root of n. Well, this is indeterminate. The base is going to infinity, right, so that tries to blow the function up, make it very large, but the exponent's trying to go to 0, and anything to the 0 should equal 1, so they compete against each other, right? The base wants to make it very large, the exponent wants to make it equal 1. Which one wins in the limit? Well, it turns out the exponent does win. That always approaches the value 1. Which means now if you're faced with a sequence involving this term, you don't have to do L'Hopital's anymore. You can just commit this to memory and remember forever this approaches 1. And here's another one. The limit as n goes to infinity of 1 plus some constant x over n to the n. Alright, so x is a constant. In this case it is anyway. We'll see in some examples in the future we're thinking of it as being variable. But here it's a constant. And this is again indeterminate, right? As n goes to infinity, the base is trying to go to 1. And 1 to any power should equal 1. But the exponent is trying to blow up to infinity, which is either trying to make the function very big or very small. But certainly not equal to 1, so they compete against each other. In the limit, this turns out to always equal e to the x. So whatever constant I have up here determines the value of the limit in this case. Okay, so this one is just e to whatever number I have right here. Again, not something you want to work out by hand every single time, just commit this to memory. And this one's kind of tricky because unless you're used to looking for it, you'll miss it the first time it pops up in problems or applications. But try to keep this limit in mind. Try to commit it to memory so that you will recognize it when you see it. And the even sort of harder part is sometimes it doesn't come in this form, right? For example, find the limit as n goes to infinity of n over n plus 1 to the n. Right, and my claim is that this has something to do with this guy, but it doesn't look at all like it, really at all. You might just look at this and say, well, this is going to 1 to the infinity, it's an indeterminate form, so I have to use L'Hopital's. But actually I can just do some algebraic manipulation to make it look just like this. Alright, so what I'm going to do is first take the reciprocal of everything, right? So I'm going to write this as 1 over n plus 1 over n to the n. Alright, that's an algebraically legal move. As long as I take the reciprocal of the inside, I can write it as 1 over this expression. And now if I just break this up into two pieces, limit as n goes to infinity of 1 over, I'm going to break the inside up into two pieces, n over n is 1, 1 over n is just 1 over n, and that's all raised to the n. Alright, so doing this algebraic manipulation, I've actually made the bottom here look exactly like this expression, where x is equal to 1. So in the limit, this is tending to 1 over e. So I highly recommend committing these two to memory, so you don't have to do this L'Hopital stuff every single time. There's other stuff from this section. There's recursively defined sequences. There are sequences involving factorials, and the problem with factorials is you can't really differentiate them. And there's the sandwich theorem or the squeeze theorem. So I'm not going through every single topic, but these are the big ideas from this section. Alright, so next up we have series. And series are intimately related to sequences, but ultimately completely separate objects, completely different. And the idea behind this is, suppose I have a sequence. Here's my sequence, 1, 1/2, 1/4, 1/8. Hopefully now you can see the pattern. You guess the next term would be 1/16, and so on. So this is just the sequence 1 over 2 to the n, where n starts at 0 and goes off to infinity. All right, so there's a sequence. I'll put curly brackets around it. Really ugly curly brackets there. That's okay. So there's a sequence. What a series is you take a sequence, you take all the terms and you add them together, right? So there's a sequence. A series would be take the sum of all of these terms. All right, so this infinite summation, which is a brand new object, right? We've never talked about adding infinitely many things together before. But this is ultimately what a series is. It's the sum of all the terms of a sequence. People tend to use big sigma notation here, so capital sigma. So this would be the sum of the terms 1 over 2 to the n, as n goes from 0 to infinity. And we want to add them all together. The problem here is, what does this mean? How do I add infinitely many things together, right? I can add up as many as I want. I can add up 1 plus 1/2 plus 1/4. I can go forever, but in my lifetime, I will never be able to add up all of them to tell you the value of this. So what does it mean to add up infinitely many terms? So the idea mathematicians came up with is, let's look at what's called the partial sums. All right, so instead of adding up all infinitely many terms, I'm just going to add up a few of them. Right? For example, the first partial sum, S1, is the sum of the first term. First term is just 1. Okay. S2, second partial sum of the first two terms, 1 plus 1/2, which is 3/2. S3, sum of the first three terms, 1 plus 1/2 plus 1/4. That is 7/4, I believe. S4, the fourth partial sum, add up the first four terms, 1 plus 1/2 plus 1/4 plus 1/8. And this, I believe, adds up to 15/8. Alright, so what you'll notice I'm doing here is I'm actually building a sequence, right? I've got this sequence of terms, S1, S2, S3, S4. It's the so-called sequence of partial sums. And my sequence looks like this: 1, 3/2, 7/4, 15/8, and so on. Alright, so this is a sequence of partial sums. The first term tells me the sum of the first term. Second term tells me the sum of the first two, then the sum of the first three. And the idea behind this sequence is that if I go further and further out in the sequence, representing adding more and more and more terms, I should be getting closer and closer to the actual value of this series, right? Not all sequences have to converge, but this sequence turns out that it does. This sequence is approaching the value 2. So as you go further and further out in the sequence, you're approaching the value 2. That means as I add more and more and more terms in this series, I'm not blowing up to infinity. I'm not approaching, or I'm not unbounded. I'm actually bounded, and I'm getting very, very, very close. As I add more and more terms, I'm getting closer and closer to 2. So mathematicians make this definition. They say that this series is actually equal to 2. And this is the way we define these infinite series. A series is defined to be the limit, if it converges, the limit of this brand new sequence of partial sums. So there's a lot here, right? It's sort of a heavy definition, but it's really important that you get these two ideas, these two concepts straight in your mind, right? A sequence is a list of numbers. A series is the infinite summation of all of the terms of a sequence. The confusing part is that series is defined to be the limit of a brand new sequence. A brand new sequence is defined from the series, the limit of the sequence of partial sums. Right, so the series is defined to be, if you add more and more terms, are you getting closer and closer to some number, is essentially the idea behind it. And one of the biggest concepts throughout the rest of this unit will be this question of, here's a series, does it converge or not? Not necessarily what value does it converge to, that's actually really hard to do in general, but just this binary question of, I give you a series, does it converge, yes or no? And we'll have lots of tests for this. Here's one of the most basic tests. It's the so-called nth term test for divergence. So I have a series, a sub n equals, say, 1 to infinity. The nth term to the test says the following: if a sub n is not approaching L, how should I write this? Let's do limit notation. If the limit as n goes to infinity of a sub n either does not exist or does not equal 0, then this series diverges. And hopefully this intuitively makes sense, right? If you think about this, the only way this can add up to a finite value is if you eventually start adding smaller and smaller numbers, right? If I keep adding, say, 1 forever, 1 plus 1 plus 1 plus 1 plus 1 forever, of course I'm going to get an infinite number, right? It's going to blow up to infinity. So the only way this can equal something finite is if you eventually start adding smaller and smaller and smaller numbers, right? So the only way this can converge is if a sub n shrinks to 0. It doesn't say that it does converge if it shrinks to 0, just that that's the only way it can happen. So here's the test. If it doesn't shrink to 0, then the terms themselves, right, not the series. It's important to get these things straight in our mind. If the terms themselves don't shrink to 0, then the series must diverge. For example, here's just a very simple example. N plus 1 over n goes from 1 to infinity. What are my terms doing? Well, here's my nth term, n plus 1 over n. As n goes to infinity, what happens here? Well, let's write this in a slightly different way. Let's write this as 1 plus 1 over n. Right? N over n is 1 plus 1 over n. What happens as n goes to infinity? Well, this is approaching 1. So essentially the series starts to look like, if you get out really, really far for huge values of n, it starts to look like you're just adding 1 forever. 1 plus 1 plus 1 plus 1. So of course this can't approach a finite value. It blows up to infinity, right? It fails the nth term divergence test. So this diverges because n plus 1 over n is tending to 1, which is certainly not 0. Right, so the only way a series can converge is if your terms eventually shrink to 0. It doesn't tell me if a series converges or not. It's just a test that can tell me if it diverges very quickly. Right, here's the famous harmonic series, 1 over n. Right, so this would be the sum of 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. It turns out here my terms do shrink to 0, right? It shrinks to 0, so it passes the nth term divergence test, but that's all that the divergence test can tell me. It can tell me if something diverges. It turns out that these terms shrink to 0, but this series also diverges, right? So this is the harmonic series. And this diverges even though even though 1 over n is tending to 0. Right? So if my terms don't shrink to 0, I diverge. If they do shrink to 0, I have to do more work. I cannot conclude that it does converge. In some sense, convergence is not a question of do you shrink to 0, but how fast do you shrink to 0. And it turns out 1 over n goes to 0 too slowly. And so there's two very important types of series that pop up in this section, telescoping and geometric. I'm not going to talk about telescoping today. We'll just do geometric series. And these look like the following. It looks like a plus a times r plus a times r squared plus a times r cubed, and so on. Alright, so a geometric series is you start with a number, and then to get the next term, you multiply it by r. To get the next term, you multiply it by r. To get the next term, you multiply it by r. So this is a series of the form a times r to the n, where n starts at 0 and goes off to infinity. This is a so-called geometric series. Oh, I shouldn't say dot, dot, dot. It equals this. Okay. And it turns out geometric series are particularly nice because I can tell you exactly when it converges and when it doesn't converge. And not only that, I can tell you if it does converge, the exact value that it converges to. And here's the answer. This converges to a over 1 minus r if the absolute value of r is less than 1. Alright, so that's all you need to know. All you have to do is check r. If the absolute value of r is less than 1, so between minus 1 and positive 1, strictly between minus 1 and positive 1, then it converges. And it converges to this value, a over 1 minus r, where a is the first term in the series, or the sequence if you want. No, it's the series, sorry. The first term in the series, and r is this geometric multiplier, right? It's the term you multiply by every time to get the next term in the series. And it diverges otherwise. Alright, so by otherwise, I mean absolute value of r is bigger than or equal to 1. So these are geometric series. They're really, really nice because it's easy to answer this question of do you diverge or not? Do you diverge or converge? And moreover, I can do something that I can't do for most series, as you'll see in the future, but I can tell you exactly what it converges to. Alright, so a very quick example here. For example, the sum of, let's say, 3 times minus 1 to the n over 5 to the n. We're going to start at n equals 0 to infinity. So this is my series. What I like to do is I like to write out the first few terms. I almost always do this for every series. So if I write out the first few terms, what do I have? N equals 0. We're looking at 3 times 1 over 1. So first term is just 3. Alright, if n equals 1, I've got 3 times minus 1 over 5. So this is actually minus 3/5. Next term, n equals 2. I've got 3 times minus 1 squared, so 3 times positive 1. 3 over 5 squared, so plus 3 over 5 squared, which is 25. And you'll notice the minus 1 up top here. Get used to this because you will work with minus 1 to the n all the time. All that does is alternate the sign, right? As we increase n from 3 to 4 to 5 to 6, it changes the sign, flips it back and forth between plus and minus. So my next term is going to be minus 3 over 5 cubed, 125, plus 3 over 5 to the 4th. 5 to the 4th is what, 625? And minus, and so on. my claim is that this is a geometric series. Right? It's a geometric series with A, the first term, is 3. And R, why is it geometric? Is because I can get the next term in the series just by multiplying by a fixed constant every single time. How do I get to the next term here? I multiply by minus 1/5. How do I get to the next term here? I multiply by minus 1/5. The next term, I multiply by minus 1/5. So my multiplier is minus 1/5. This is between plus or minus 1, right? The absolute value of this is less than 1. So I know it does converge. And I know it's going to equal A, 3 over 1 minus R. 1 minus 1/5. Which is 3 over 1 plus 1/5, so 3 over 6/5. Which is 15/6. And so just by recognizing this was a geometric series, I was able to answer this question very quickly. Does it converge? Yes. And I can tell you exactly what it converges to. So the last big topic in this section is telescoping series. The idea is you can rewrite your series in such a way that all of the middle terms cancel out, and you're just left with a first term and a last term, or a first 2 terms and the last 2 terms. But we'll stop this section here, and we'll move on to the next one. All right, so last up we've got the integral test. All right, so what does the integral test say? It says this. It says suppose I have a sequence. Suppose a sub n is a sequence. And it's more than just any old sequence. I'm requiring here that I only have positive terms. So it's a sequence of positive terms. Right, there we go. It's a sequence of positive terms. If a sub n, remember what a sequence really is, it's a function. It's a function defined only on the natural numbers. So if a sub n is a function f of n, where I'm actually going to allow this to be a continuous function in this continuous variable x. So instead of having n for the natural numbers, just 1, 2, 3, 4, 5, 6, and so on, I'm going to think of this as a continuous function over all of x, f of x. So where f of x is a continuous, positive, and decreasing function. Not necessarily for all values of x, but just eventually this happens. So eventually I make x large enough where it's always positive and decreasing. Where this is a continuous positive decreasing function of x. Then the integral test says the following. Then the series, the infinite series a sub n, going from 1 to infinity, and the integral of this function, the improper integral of f of x from 1 to infinity, these do the same thing convergence-wise. So they either both converge or they both diverge. These either both converge or both diverge. Which shouldn't come as much of a surprise, right? Series are just these infinite summations. Integrals are really summations, so the area under this curve should have something to do with this sum over here. And it turns out the way they're related is they either both sum up to a finite area or they both sum up to an infinite area. So they either both converge or diverge. So this would be one of our tests that allow us to answer this question of if someone gives you a series and you're asked this binary question, does it converge or not? Well, as long as your series consists of terms that are decreasing forever, then instead of studying this, you can study this integral and ask, does that converge or not? Because the answer to that question will be the same as the answer to, does this series converge or not? And as we go on through this class, we will have lots of these tests, lots of these tests for convergence of a series. Full disclosure, this is kind of one of the least important ones. It's one you'll use most infrequently because there's really only one time that you really need to use it. So for example, does the series let's see. Yeah, let's do this one. Does the series n equals 2 to infinity of 1 over n times ln of n, does this converge? Notice I'm starting here at n equals 2. That's because if I plugged in n equals 1, I'd be dividing by 0, right? So my series is going to start at the n equals 2 term. So instead of studying this series, so we're going to instead study this improper integral from 2 to infinity of 1 over x times ln of x dx. Right, this is one of the very few times in this unit where something that we've studied previously will come into play. Here we've got improper integrals, right? This is another calculus 2 topic. So we're going to look at this integral and ask, does this integral converge or not? Right, notice, by the way, my function is exactly the same as the original function. I've just replaced n with this continuous variable x instead. That's all you ever have to do here. I will very quickly point out that this is indeed a continuous function. It's always positive, and it is indeed decreasing as x gets bigger. This function is getting smaller. So the integral test does apply here. And let's see, we're going to study this. So it's improper. First thing I'll do is I'll just replace that upper bound with b, and take the limit as b goes off to infinity of 1 over x ln of x dx. Next thing I'll do is what? How do we integrate this? Oh, it looks like it should just be a pretty easy u substitution, right? We'll let u be ln of x, right? Then du is 1 over x dx. 1 over x dx, there's my du looking me in the face. So this is equal to the integral limit as b goes to infinity of the integral of 1 over u, 1 over u du. Remember that I do have to change my bounds here. So if u is ln of x, x is 2, my bottom bound is ln of 2, and my upper bound, if x is b, u is going to be ln of b. Alright, so we've transformed this integral into 1 over u, and things are looking pretty good now. This is the limit as b goes to infinity of integral of 1 over u is ln of u from ln of b to ln of 2. And we're going to have lots of natural logs here. This will be the limit as b goes to infinity of ln of, let's see, let's write this in a nicer way, ln of b minus ln of 2. So what's happening is b goes off to infinity. By the way, I should probably have another bracket there. Well, as b goes off to infinity, natural log, it grows to infinity as well, just very, very, very slowly. So ln of b is growing off to infinity. Ln of infinity is still infinity, so this is looking like infinity minus some constant, right? So the answer is that this integral diverges, right? It's equal to infinity. It's got infinite area under the curve. This integral diverges, so by the integral test, so does this thing. So we've shown that this, I'm totally out of space, this guy diverges. And the integral test says the series and the integral have to do the same thing. So this one also diverges. As you develop more tests, you'll find you use the integral test less and less often. This is really the most important case of it when you've got some sort of natural logs down the denominator. It turns out the integral test is useful. But we'll stop here. Thanks, guys.